Hi guys, welcome to the second video. The last video we learned about faults and how they produce earthquakes and a little bit about the earthquake cycle. In this video we're going to look at a topic called Paleo-Seismology, and that is literally how geologists identify faults in the landscape and assess whether they're hazardous or not. And specifically, assessing whether they're hazardous usually means determining when the last earthquake occurred on this fault, and maybe how frequently earthquakes occur, and how big those earthquakes are likely to be when they do occur. So why is this important? Well, of course, earthquakes are dangerous, and if we can develop predictive models for earthquakes, we can actually save lives. From a broader standpoint, also understanding how earthquakes and faults are related gives us a deeper insight into the mechanics of the crust and the kind of physics of how the crust deforms under the stress of plate motion. So let's motivate this a little bit more. Why would we want to know the detailed earthquake history of a given fault? Well, unfortunately, humans have a way of expanding and building infrastructure in nature, and often that infrastructure gets built across active faults, especially in the western US. So this is an example of a before and after shot of a development that went in outside of Salt Lake City. So here in 2004, we see this kind of foothills area isn't developed yet. Just a few years later, there's a big elementary school here, as well as a bunch of new houses and developments. So this is all fine, except this red line is an active normal fault that's cutting across the landscape. And obviously, developers hadn't recognized this prior to development, so they built this elementary school literally right across the fault zone. Now, if a big earthquake occurs here, it could physically damage the building, even tear it in half, and of course, the seismic waves themselves could also shake everything really violently. So this is a hazard, and ideally we'd like to know this hazard before we build, but also now that we've built, it's prudent to try to study this fault and figure out when and how big earthquakes are going to be on it. So to illustrate what a normal fault earthquake might look like in Salt Lake City, I wanted to show you a quick video. And what's cool about this video is that it's done to scale, and it shows a normal fault earthquake where the fault is running along the flank of this mountain range, and the basin out here is the downdropped block. And one of the remarkable things you'll see here is the scale. And you'll really note that human-built infrastructure, like buildings or schools, are just tiny in comparison to the scale of crustal blocks and the amount of energy that is released. Literally, these things would get thrown around like dollhouse furniture. So let's watch this video here. So the stress is building. Here comes the earthquake. That hanging wall drops down. The seismic energy is released. In this case, being picked up at seismic recording stations, but of course also destroying any structures that are right in the area. So with that motivation, what are we going to learn in this video? We're going to learn how to identify faults in the landscape, and then we're going to learn how to determine the number of past earthquakes that have occurred on those faults and when the next earthquake might be coming. So how do we visualize faults in the landscape? Quite often they appear as cracks or fractures right after an earthquake, and then often you'll see larger fault scarps. These are large slopes, linear slopes, that show where one crustal block has been separated from another crustal block, sometimes creating vertical relief on the scale of tens or hundreds of meters. Now, geologists would often want to know how active is a fault. And one way to assess that is to look at how that fault is cutting through active surface features like river channels. Okay? So here's a shot from the San Andreas Fault in California, and you can see that the fault itself has offset this river channel. This piece of the channel used to line back up with its headwaters, and it's been offset and shifted 100 meters or so to the left. So we see that in the photo, and then here in a high-resolution LiDAR-derived hillshade image. So one thing geologists can do is ask, what's the long-term slip rate here? And that's given by measuring the offset distance and dividing it by the age of the river channel. And that might allow us to say, okay, if this fault has moved 10 meters in 10,000 years, then the long-term slip rate is 1 meter per 1,000 years. And that's useful information when we're thinking about seismic hazard and the distribution of faults. We're going to see a little later that dating the age of this river channel then becomes the problem. How do we actually know how old this river channel is? And one way to do that is to use carbon-14 dating of deposits associated with this river channel. But now you'll notice the one thing we haven't gotten out of our long-term slip rate is any information about how many earthquakes occurred in order to accomplish this offset. Was this formed by 2 earthquakes, by 10 earthquakes, or 20? And that's really important information in thinking about how often they occur and also how big they're going to be. So I want to transition now into learning about how we determine the number of past earthquakes. And there's a few different ways to determine earthquake recurrence, but the most common is to study sediments that the earthquake is cutting through. And the basic premise of this approach is that each time there's an earthquake, the fault zone is going to rupture through the surface and actually rupture the overlying sediments. So let's walk through this for a second. Picture this. Picture you've got a layer of young sediments. Okay, so these are older sediments on the bottom, and then younger sediments have been deposited on top, maybe during flood events, for example. So these sediments are just sitting here before the earthquake. Then the earthquake occurs, and the strand of the fault comes up and actually offsets and maybe drops the right-hand side down a little bit relative to the left-hand side. Now that offset is actually recording the earthquake event. And then over time after the earthquake, we start to cover that in sediment. Maybe there's another flood event or a wind event that buries the whole thing in sediment, but you see this overlying sediment layer is no longer uniform in thickness. It actually changes thickness. And particularly what we get here is called a colluvial wedge, a little pocket of sediment that's filling in a wedge-shaped area right at the fault scarp. Okay? And what's important is that now, of course, more sediment's going to keep being piled on, and we're going to continue to get, and when the next earthquake occurs, it may rupture through the same place, or that strand may rupture in a different place. And this gives us a basis upon which to reconstruct earthquake events. Now, how do we actually see these sediments in cross-section? The basic technique we use is called trenching. And we literally go out and take a backhoe and dig a long, deep trench, usually perpendicular to the fault. So in this case, the fault is running left to right across your screen, and we've got 4 trenches dug across it. And here's an example of what you might see in one of those trenches. Geologists would get in there and make very careful observations of where the fault strands are coming up through the sediment. So this is always a complicated process, and we're going to really simplify it here. But each of these red traces shows a fault strand that's come up and fractured through the surface. This strand here is the main one. And what you can see is that the right side is dropped down a little bit relative to the left side. And if you look closely, you'll see kind of some gravel unit coming in here. That gravel unit ends, and then we pick up this lighter colored sand. And so this sand is actually the colluvial wedge. It's the area that was filled in with loose sediment after the right-hand side dropped down. And again, the approach to this, to ask, okay, when did that happen, we would actually try to find datable material within the sediments, specifically organic material that we might be able to date with carbon-14 techniques. Another major question in this game is, where should you dig? And obviously you need to dig in a place that has active sedimentation, where sediment is actively ponding so that you're laying down new sedimentary layers across the fault. Nowadays, we can identify locations like this using high-resolution topographic data called LiDAR data. And we can create very detailed renderings of the landscape. So here you see a road coming through here. Here's a creek coming through here. Some bushes and trees in here. And the place that was picked to trench is right here. Because we have a couple drainages coming out, and they're going to be washing sediments into this little ponding area where we're going to get a nice layered sedimentary succession that we can trench into. And this has been done on a number of faults in the western U.S. and in the world. One of the earliest and most successful examples was developing fault chronologies along the San Andreas Fault in Southern California. And this plot shows the result of those earthquake chronologies on one specific section of the San Andreas. So along the x-axis we see the number of earthquake events, and then along this axis we see the timing of the earthquake event. And in this case we can see that these earthquakes aren't perfectly spaced in time. We have an earthquake here at like 695, another one here at maybe 730, and another one here at 770. So we've got 3 earthquake events in the space of less than 100 years. Then we've got a long gap here where maybe almost 200 years goes by before the next one. And we've got a few more clustered here. Then we've got long recurrence intervals, and then we've got some more clustering. So we can see from this record that the idea of a perfectly consistent recurrence interval isn't necessarily realistic, but the more detailed chronologies we're able to develop, the more precisely we can constrain the timing of future earthquakes. So I'll leave you with these concept questions, and also please go online and take this brief quiz, and we'll see you shortly for the next video, which actually is going to be about subduction zone earthquakes, not paleoseismology.